Yeah, I think that
So
was
our
helpful.
next speaker is Elliot Ronaghan, who is going to speak about recent InfiniBand optimizations in CHIUW.
All right, I should be screen sharing now. Let me know if you can see that and if you can hear me.
Yeah, it's working for me.
All right, so welcome everyone. My name's Elliot Ronaghan, and I'm a performance engineer on the CHIUW team. Today I'm going to be talking to you about some recent InfiniBand optimizations in CHIUW. And at least to me, this is some really exciting work despite the really boring title. I always really struggle to come up with catchy titles. My backup for this one was going to be To the Moon with Apollo, where Apollo is the name of HPE InfiniBand systems, and To the Moon for all of the recent meme stock stuff. But I couldn't quite bring myself to use that title, so here's where we end up. So coming on to slide 2 here, I just wanted to give kind of a hook or a teaser for this talk. And kind of the main theme of this is going to be that some recent optimizations have significantly improved CHIUW's performance and scalability on InfiniBand. So at the high end, we're seeing something like a 15x performance improvement for Arkouda ArcSort on a system with 240 nodes, roughly 30,000 cores. And so this graph shown here is a performance scalability graph. And so performance meaning higher is better, and scalability meaning that on the x-axis going to the right is increasing the number of locales or the number of nodes. And this is again for Arkouda ArcSort. This is on an HPE Apollo system with 100 gigabit per second HDR InfiniBand. And there's 2 lines on this graph. In the light blue towards the bottom, we have performance with CHIUW 123, and the dark blue towards the top is CHIUW 124.1, which includes the optimizations we're going to be talking about today. And kind of looking at this graph, what we see is that in the light blue line, performance up to 64 nodes was pretty good before, but it really fell off after that. And kind of 64 nodes was the kind of the scale that we were running at previously before this work. And then we can see that with these optimizations, performance even up to 64 nodes is better. But more importantly, we see that we continue to scale and performance improves as we continue to add nodes. So moving on to slide 3 here, just some kind of background for CHIUW's use of InfiniBand. And I think this is something Brad mentioned during his overview, but historically, the CHIUW team has really focused on performance for Cray networks, particularly the Cray Aries network, where our intent was to ensure that CHIUW had the right language features and semantics first, and then optimize for other networks. So basically demonstrate that CHIUW as a language could perform well on the Aries networks, and then over time, expand that to other networks. And so we've done pretty extensive optimizations for Aries networks. And so more recently, we've shifted our focus towards improving performance for InfiniBand. And this is something that was kind of the natural next step anyways, but the HPE acquisition kind of accelerated this because it gave us access to some significantly larger InfiniBand systems. And then to target InfiniBand, CHIUW uses the GasNet communication library, and specifically we use the IBV conduit. And for this talk, I'm going to refer to that as GasNet IBV. On slide 4, delving into that a little more, delving into GasNet IBV a little more. So something that's important to note for InfiniBand and kind of HPC networks in general is that memory has to be registered with the network in order to do one-sided gets and puts, also known as RDMA, or remote dynamic memory access. And basically what that is RDMA allows you to directly read or write to a remote node without involving the OS kernel. And this is something that's really important for performance in CHIUW applications. And so because memory has to be registered, you have to figure out how you want to do that. And GasNet IBV supports 2 distinct registration modes. There is a static registration mode where all memory is registered at startup. And this results in fast communication, but it hurts NUMA affinity and it can lead to long startup times. And then there's dynamic registration where memory is registered at communication time. And this can hurt communication performance, but it results in good NUMA affinity and fast startup times. And CHIUW defaults to dynamic registration to get good NUMA affinity and fast startup times. We believe this is the right choice for most users getting started. In the past, we had recommended static registration to some users with certain communication-heavy idioms, but this isn't really ideal. Ideally, we really just want to have one mode with no or few downsides like we have for Aries networks. And then late in the 124 release cycle, we identified the root cause of some of these InfiniBand performance issues. And we were able to somewhat improve NUMA affinity and startup times for static registration, but that won't be covered in this talk. And then the focus for this talk is that we were able to significantly improve communication performance for dynamic registration. And these improvements were motivated April's 124.1 release, because we thought it was important to get these into the hands of users kind of sooner rather than waiting for the 125 release. And so starting to delve into some more of the dynamic registration background on slide 6 here. So I think I mentioned this already, but GuessNet IBV dynamic registration only registers memory at communication time. And because you don't have to register at startup, that means that startup time is fast, and NUMA affinity is based on the user's first touch instead of being a side effect of registration. But something that's important to note is that memory registration is an expensive operation, so you really want to amortize that cost. Ideally, you want to register a given region of memory once and then reuse that registration. But this reuse requires tracking which memory regions are currently registered. And that tracking is what we ultimately discovered was the bottleneck. So what we identified was there was a bottleneck in the registration tracking code that was limiting performance and scalability. And kind of the core issue here was that we were running out of dynamic registration entries, and this led to deregistration and re-registration cycles, which prevented amortization. And so kind of what would happen is during a program run, we would be going to do communication, and we were out of dynamic registration entries. So we would have to evict an old one from the cache and slot the new one in. But then shortly after that, we would be doing communication with that old region again. And so then we'd have to evict something else and re-register ours. So we just kind of got into these really bad situations where we were just endlessly deregistering and re-registering things. And then we were paying the registration cost for every communication event, which is what was killing performance. And so to resolve this, we collaborated with the GasNet team. Kind of at a high level, the solution here was to increase the number of dynamic registration entries, and it's now based on an execution time query of the hardware capabilities. And then there were some significant improvements made to the data structures that are used to track which regions are registered. I'm moving on to some of the performance results of this on slide 8. So these first couple of graphs that I'm going to show are from our nightly performance tracking. So this is something we run every night and then kind of look at the performance results once a week or so. And I'm going to start off with kind of the most simple benchmarks and go into kind of more interesting applications and then user applications. And so on this first slide, we're starting with serial transfer performance. This is basically large point-to-point transfers. And this top graph is a large get of an array. And the graph is pretty busy, but breaking it down, there's kind of 3 transfer sizes happening here. So in green, we have 1 gigabyte transfers. In purple, we have 1 megabyte transfers. And in blue, we have quarter of memory, or for this particular system, that's 48 gigabyte transfers. And then in the dashed lines, we have static registration, and the solid lines are dynamic registration. And so what we see in purple is that dynamic registration performance was always close to static registration performance. And what's happening here is that this particular test has a 5-second trial loop. And so on the first trial, we register the memory. And then for subsequent iterations or subsequent trials, we're able to reuse the registration. So you really don't pay much overhead for the dynamic registration in this case. But in blue, looking at the 1 gig case, we can see that even at relatively modest transfer sizes, we were already starting to hit that registration and deregistration cycle. And so with that fixed, now we see that the solid green line is pretty close to the dashed green line. So dynamic performance is now pretty close to static. In the blue line, we see that this is a 48 gig transfer and performance was somewhat improved, but it's still pretty far behind static registration. And this is because in the first trial, or this is because the 48 gig transfer takes more than 5 seconds. And so we really only get 1 trial. And so we see the overhead of the registration there. But overall, much better spot than we were in. And the bottom graph is just the symmetric thing, but for large puts. And so moving on to the next slide, we get into some more interesting benchmarks here. And these are codes that do all-to-all communication patterns. This top graph is for NAS Parallel Benchmarks FT, which is a distributed FFT application. And so focusing on the green lines, we can see that dynamic registration now performs better than static registration. This is a code that cares about both NUMA affinity and communication performance. So We have good communication performance now and better NUMA affinity, so performance is ahead of static registration. And then on the bottom graph for ISX, we see similar results where in blue, we see that dynamic registration is nearly on par with static registration. So performance is better than it was, but there is still some work to do there. And then on the next slide, we start getting into user applications. So we see significant performance improvements for Arkouda. And so this is for core idioms like argsort, group by, and then we get into set operations. And Ben McDonald will be talking more about set operations in a talk later today. And then that's kind of it for the 16 node, kind of the small scale studies. Next, I want to move on to talking about scalability and Arkouda in particular at scale. And so if you're not familiar with it, Arkouda is a library that provides NumPy-like arrays at HPC scale. So it's basically a NumPy or Pandas Python front end that's backed by CHIUW. And as you saw in the previous slides, we track Arkouda performance nightly at small scale, but then we had an opportunity to run on a much larger HPE Apollo system, where this system has 128 cores per node, which is dual 64-core AMD Rome processors, and 2 terabytes of memory per node. And they're connected with 100 gigabit per second HDR InfiniBand network. And so on this slide, we come back to kind of the graph that I showed as a teaser, or at least part of it, where previously performance was falling off above 64 nodes for argsort, and other core idioms like gather and scatter were also impacted. And so what's happening kind of behind the scenes here is that Arkouda uses aggregation to get good performance, and that's because fine-grained communication does not perform well on InfiniBand. And so we're aggregating things and doing a lot of concurrent gets and puts. And what was happening was after we got above 64 nodes, the number of memory regions we were communicating was increasing. And we just ran out above 64 nodes, and that's when performance really started to fall off. And so with that resolved, with the dynamic registration fixes I talked about, what we see is that argsort is about 50% faster at 16 nodes, and 15x faster at 240 nodes. And we see similar results for other idioms like gather and scatter, which are also using aggregation under the covers. And next, I wanted to give some more examples of argsort performance at different scales and problem sizes. But to do that, I wanted to give a little bit of context for argsort. So something that's important to note is that argsort requires about 6 times the input data for scratch space. So if you're sorting 10 gigabytes of data, you need about 60 gigs of RAM for the scratch space there. And previously, the Arkouda scalability graphs I've shown up to this point have been using 8 gigabyte per node input arrays. And that's just because it was the largest power of 2 that we could reliably run on an internal XC. But this Apollo system with 2 terabytes of memory allows for much larger problem sizes. And something that's important to note is that argsort has a fixed startup overhead that depends on the number of cores times the number of locales. And so because this Apollo system has more cores, that means that there's higher startup overhead. And so going into some of those graphs, so this is going to show the Apollo system versus an XC. And on this graph in light blue, we have the XC. In dark blue, we have the Apollo system at 8 gigabyte arrays. And in the dashed dark blue, we have 64 gig arrays. And what we see is that for equivalent problem sizes, there's around a 2.5x improvement at 16 nodes for the Apollo system over XC, and about a 50% improvement at 240 nodes. And the reason that we only have the 50% improvement at 240 nodes is because of the startup overhead. But once we get up to larger problem sizes where that startup overhead matters less, so using 64 gig arrays, we see around a 3x performance improvement for the Apollo system over XC at 16 and 240 nodes. And just kind of expanding the problem size even more. So we can run really significantly larger problem sizes on Apollo. So this final graph shows performance at 256 gig input arrays that ends up being 1.6 or 1.7 terabytes of memory per node. And we can see on the graph in the dotted blue line that performance doesn't increase significantly because we've already kind of paid that startup overhead. But kind of at the high end here, what we're seeing is we're able to sort around 225 gigabytes per second. And that translates to being able to sort 60 terabytes of data at 240 nodes in just under 5 minutes. And so that's really what I have to show for today. Just kind of the summary is that, there's been some significant performance and scalability improvements for large transfers on InfiniBand systems. This dynamic registration is nearly on par with static registration while retaining the other benefits like fast startups and good NUMA affinity. Going forward, we want to continue to improve dynamic registration, catch up for those cases that we're behind still like ISX. And there's also alternative registration mechanisms like on-demand paging that we want to look at, where on-demand paging is a hardware and firmware solution to on-demand registration, instead of what we're doing now, which is tracking in software. And then kind of longer term, looking at improving other aspects of InfiniBand performance, looking at improving things like network injection, which is currently serialized, which limits the performance of fine-grained communication and was one of the original motivating reasons for adding aggregation in the first place. And we expect that mapping to the upcoming GasNet-EX multi-endpoint API should resolve that. And we want to look at some other things like targeting the GasNet-EX network atomic API. And that is all I have for you today. Questions?
Thanks, Elliot. Really nice presentation. We have 4 questions here. Just to mention for people who are not looking in the chat, all the questions are staying during the session, so I'm gonna read them from the oldest one to the most recent. So we have a question from Tiago Carneiro. Are there huge performance differences in if one uses OmniPath compared to these new InfiniBand features?
Yeah, so OmniPath is interesting. So OmniPath was kind of a sibling to InfiniBand that Intel created, but Intel has killed that line off. So it's not something that's really actively developed anymore. So for InfiniBand, I think you end up using GasNet OFI to target it, and that is not something that was improved by this work. And technically, you can target OmniPath with the Verbs API, which is what IBV is, but I have not done any experiments myself there to see if you would see benefits.
Okay, next question from Mathieu. Are you planning to optimize network atomics for InfiniBand systems?
Yeah, that's definitely something that we want to look at targeting with the GasNet-EX API that supports that. A little bit of a challenge there is that, so like the Aries network supports all of the atomic operations that CHIUW cares about, but InfiniBand is actually relatively restricted, so it only supports things like compare and swap and I think maybe increment and add. So I think there's a question of how do we effectively target a limited API? And so we might need, some new language level support for saying like, hey, these are the operations I want to use on atomics. And then we can decide if those are all supported in the network atomic stack, or if you have to fall back to processor atomics in some cases. But it's definitely something that we are planning to explore.
Okay, next question from Paul Casella. Was a static registration occurring outside of the timed region in the first set of performance tests?
Yeah, that's a really good question. And it is occurring outside of the timed region. So these graphs show just the kernel timing. And so anything outside of that was not included. So if you did a whole program timing, I think you would see similar performance results.
Okay, then the last question from John Artman. What is the distinction between the solid and dashed lines in the first set of graphs?
Right, so the distinction there is just the static versus dynamic registration. So the solid lines are dynamic registration and dashed is static. And on the graphs, they're labeled as GasNet IBV fast versus large, where these are the names we use in nightly, but fast maps to static registration and large maps to dynamic.